We get perfect. Okay, yes. Welcome to the Data Academy session for difference images and light curves. So if you're into time domain astronomy, this session has some good information for you. All right, we're here. We're at the end of the morning session on Wednesday. There's going to be a drop-in Q&A session right after this. So if you've run into any troubles with login or trying to do things during these first sessions, do stick around after this session. We'd love to hear what you're having trouble with or hear your extended questions and discuss them in our drop-in Q&A. As a reminder, we have an exit survey. The survey is per session, so we do want to hear from you about every session. The survey is anonymous. It's very short. It just asks you which session, how useful the session was, what did you learn in this session particularly that was helpful, and then what other content would have helped you prepare. We will use all of this feedback to redesign Data Academy for next year. As another reminder, if you can't stay for the drop-in Q&A or you run into problems or questions later, the Rubin Community Forum at community.lsst.org is the place to go. It is our help desk. Any and all kinds of questions or problems are welcome in the support category. Just come to this URL. You will have to make an account. It's a separate account from your RSP account. There's no restrictions. For example, for data rights holders, anyone can make an account in the forum and post questions here, and we will get back to you. We would love to hear what you're having trouble with and help you get through it. As another reminder, everything that's in today's session is available in the Data Preview 1 documentation at dp1.lsst.io. That documentation, in addition to information about all the data products and versions of the tutorials, it also has the details for how to cite Rubin's Data Preview 1 if you do use it in a paper. If you are looking for more general information about Rubin Observatory, we don't talk about the survey itself actually very much in the Data Academy. So if you're looking for details about the camera or the survey or anything else about Rubin Observatory, it's the For Scientists section of rubinobservatory.org that you should head to. All right, session number 9, difference images and light curves. Today, we're going to be doing a few hands-on tutorials about the difference images and the associated tables that contain photometric measurements of the sources in those images, also known as light curves. We're going to cover the data processing steps that create the difference image analysis data products, the difference images themselves, and the DIA source object and force source tables, as well as the solar system object table. We'll touch a little bit on solar system stuff here and there, but mostly if you work in the time domain, and in particular on moving objects, solar system objects, then tomorrow's session on the solar system data products is the one for you. After a couple slides, we'll do some hands-on tutorials. All right, some key concepts around difference image analysis. DIA in particular stands for difference image analysis, and there are a couple of key concepts are template coad images, image subtraction, and difference images. So a template coad image is a combination of the third best seeing visit images. So for Data Preview 1, all of these visit images were taken over 7 weeks at the end of 2024. The 33% of them that have the best seeing, the best image quality, are stacked together to make good seeing template coad images. Image subtraction is when this template that's created is subtracted from a visit image to create a difference image. Just to go back one slide. Up here in the corner, these are examples where science is the new or visit image. The template image is the image that is made from all of the best seeing, best image quality images. And then the difference image is created by subtracting this template image from the science image. For Data Preview 1, it's very important to understand that this process, because Data Preview 1, again, just 7 weeks at the end of 2024, using the 33%, the third of the visit images that were obtained over 7 weeks as the template, that's a little abnormal for time domain science. Usually you make template images out of older images that were obtained, for example, the year before. And in the future, once Rubin Observatory is in sort of steady state and we're having annual data releases, that will be the case. The templates will always be an older image. Time domain objects, transients, moving objects won't appear in the template image because the templates will be made out of old images. But because Data Preview 1 was obtained over such a short time scale, the templates are made out of the same images that you're making the difference images out of. This means that objects like supernovae and like moving objects, they do appear in the template image. And then when you do image subtraction, that messes it up. You don't get as always such a nice, clean difference image. It can cause problems. So just keep that in mind. I don't think I have an example specifically to show you today, but I'll try to mention that a few more times. That this is different from how it will be in the future, and it does cause some problems sometimes. No, we will have an example actually that you'll be able to understand why this is an issue. All right, key concepts: template co-add images, image subtraction, create the difference images. Altogether, the creation and analysis of difference images is DIA. So wherever you see DIA in any of our data products, processing descriptions, it always stands for difference image analysis. More key concepts. We have the three terms here: the DIA object, SS object, and DIA source. With LSST, object and source have very specific definitions that might differ from time domain surveys that you might have experience with in the past. So for LSST, a source, a DIA source, or any term source where you see it, it's a signal to noise ratio greater than 5 detection on a single image. If you see just a source table, then that's a detection in the direct or science or visit image. All of these terms are interchangeable, direct, science, and visit image. The DIA source, it's the detection on a difference image specifically. So source always refers to detection in a single image. Whereas object is the term that we use for the actual astrophysical transient or variable at a static sky coordinate. So objects are always things that can appear in multiple visit images, but have they just kind of correspond to one physical astronomical source, one transient or variable. If it's just simply the object table, which we had a different session on, then it's one galaxy or one star. The DIA object table, it's one transient object at a particular static sky coordinate. The SS object, it also refers to the astrophysical objects, not just the detections of them, but the SS stands for solar system. And so the SS object is a moving solar system object that has a set of known orbital parameters. So source is always a detection in a single image, and object always refers to the actual physical source. In this case, too, these terms, the DI object is a table. So we would say the DI object table is the table that contains all DI objects. Or if we're talking about a single DI object, it's one single astrophysical time domain object at a given sky coordinate. All right, that's the key concepts of object and source: DI object, SS object, and DIA source. All right, so whereas sources are always detections with a signal to noise ratio greater than 5, for a lot of science goals, you instead used force photometry. So in general, force photometry means a measurement that's made at a fixed coordinate in an image, regardless of whether an above threshold, regardless of whether a signal to noise ratio greater than 5 source was detected in that particular image. So for example, we have a table called force source on DIA object. And what happens in that table is for every sky coordinate where we have seen a transient or variable object, so for every DI object go back through every difference image and every visit image and do force photometry to measure the flux at that particular location at that particular time for that visit or difference image to build up a forced photometry light curve. These are the ones that we recommend that you use for science, not just detections only. With science, you get the full measurements of that object in every single image that we have. You get it from the forced photometry table. I'm going to show you the difference in an example later on. Two more key concepts, of course, light curve and a time series feature. Light curve is probably a term you're already familiar with. It's just a plot of brightness over time, for example, magnitude or flux as a function of date. And then time series feature, these are statistical measures that are derived from the light curve itself. So the mean or the standard deviation of the fluxes, the slope of the flux over time, skew. You can measure lots of different statistical features of the light curve, and together collectively, the ones that Rubin pre-measures for you for all DI objects, for example, are called time series features. All right, to approach sort of DIA from a standpoint of putting together a narrative of the processing that generates the data preview one imaging catalog data products related to DIA. This is kind of the story of how it happens. So new image is obtained at the telescope. That image comes off and it goes through like the ISR processing for visit images that you just heard about earlier today. Then that image has a template cut out of our large all sky template that is the same dimensions as the new visit image. That piece of the template image is warped, scaled, and PSF matched to the visit image. This is done with an implementation of Allard and Lupton 1998 that's used for PSF matching. A lot of work has been done since then, actually. So it's not exactly the same, but it's a very modern technique, yet similar, doing the PSF matching. Then once you have your warped and scaled and PSF matched template image, you subtract it from the visit image and the product is a difference image. One difference image per detector per visit. All right, once we have the difference image, that's when source detection happens. Positive and negative sources with signal to noise ratio greater than 5 in the difference image are all detected. PSF fluxes are measured for all detections, and these become the DIA sources. They go into the DIA source table. So DIA sources, all detections. Then that detection in the difference image is associated with either a static sky DIA object. So if we've seen something at that location on the sky before, and a DIA object already exists at that location, the DIA source is associated with it. Or if nothing has been there before, it becomes a new DIA object, so long as there's not a known solar system object that we expect at that exact location at that time. If that is the case, if there's a known solar system object that is predicted to be at that location, then that is what we've detected instead. So the DIA source gets associated with the solar system object instead. After the association phase, then light curve characterization is redone. So for example, if we've added a new detection to a DI object that we've been seeing for months, all of the time series features, all of the statistics for the light curve get recalculated to account for the new detection. And the products of this process of detection, measurement, association, and characterization, this data all goes into the DIA source, DIA object, and solar system object tables. At a later time, the force photometry happens, where we go back through every visit image and every difference image and do force photometry at the locations of all of the known DI objects. And then that produces the force photometry light curves that are stored in the force source on DI object table. All right, so that's kind of the story of how difference image analysis is done and how the various difference image analysis DIA data products get made. Just to take a little bit of a closer look at each one of these data products, let's talk more about difference images, kind of in a practical sense. The difference images can be accessed via the Butler the Simple Image Access Service, the SIA service, and the Table Access Protocol, the TAP services. I've heard all about these over the last couple of days. The specific Butler dataset type, if you're querying for difference images in the Butler, is just difference underscore image. They can be uniquely identified by their detector and visit. And then if you do get a difference image back, what you're getting are three two-dimensional arrays of pixel data. One of the planes is the image plane. It's the sky pixel data, like the flux units in nanojanskis. Every image also has a variance plane and a mask plane that helps you understand the processing that's happened to those pixels. Every image also comes with metadata, header metadata about the state of the observatory at the time, the PSF, photometric calibration that was applied to convert like the instrumental fluxes into nanojanskis, and of course the WCS, which is the World Coordinate System. This is not unique to difference images. All of Rubin's images come with basically the same set of information. For the DIA source table, for accessing that particular one, you can access it via the TAP service or the Butler. If you're using the Butler to access the DIA source table, its dataset type is DIA underscore source. And if you do go to the Butler and ask it for DIA sources, you will get them by tracked. And tracked must have been covered in another session by now, but basically it's a chunk of the all sky tessellation of sky. So we take the whole sky, chunk it up into tracks, and then each track is further like chunked up into 100 individual patches. And it's just kind of how we refer to places on the sky. So if you get DIA sources from the Butler, you get all the DIA sources for a given tract, like a chunk on the sky. Within the DIA source table, if we want to talk about key columns, there are a couple of unique identifiers. So the DIA source table, every row has a unique DIA source ID. And then to go with every DIA source, you also have the ID of either the DIA object or the solar system object that it was associated with. There's, of course, other like information about the visit detector, like I mentioned before, the band that the DIA source was detected in, the time of its detections, coordinates, the fluxes in both the difference image and the direct or science image, plus a variety of flags, such as the is dipole flag. We're not going to discuss flags today in this particular session, but if you're interested, I can point you to the documentation and some of the recommendations for flag usage to sort of clean your data and choose only good detections. We can tell you more about that later. To take a closer look at the DIA object table, it is also accessible by either the TAP or the Butler services. Within the Butler, it is also chunked up by tract. And so if you get the DIA object table, it will be for a given tract. The unique identifier, of course, DIA object ID, one unique identifier goes with one set of coordinates on the sky. And then it has the time series features in it. So you don't have like it's not the same sort of flux and time measurement. This is these are properties of the light curve, properties of the object itself. So a few of the time series features are things like the minimum and maximum flux, mean flux, standard deviation of the flux, and a bunch of other things. And then the force photometry table, fairly similar to like how a source table is set up. It also is available via either the TAP service or the Butler, with very similar measurements as the source table. The one thing that is different about force source on DIA object table is that it doesn't have the time. Like, it doesn't have the modified Julian date of every single measurement, but all that means is you have to join it with the visit table to get times out, and I will show you how to do that in the demos today. Speaking of the demos, we have a lot of tutorials that are related to time domain science. This is my sort of suggested learning journey for getting started with time domain science. You'd start off, like if you did want to plan a little curriculum for yourself, start off in the 100 level, get an overview of the data services, but then mostly you're going to be querying probably most of these catalogs with the TAP service. So getting familiar with the TAP service is recommended. Then you would work through the 200 level tutorials, one per data product. So you'd work through each of the tutorials that is designed to teach you all about the data products that I just mentioned, the different catalog types and the difference images. And then you would turn yourself to the 300 level science demos. For there, you'd probably want to start with our Data Preview 1 overview just to kind of understand the Data Preview 1 data. And then from there, pick whichever series of the 300 levels most closely matches your science interests. If you're not a JupyterLab user, not a Python coder, there's also this recommended series for portal tutorials that you can follow to figure out how to navigate the user interface all the way up to creating light curves for variable objects. All of these tutorials you can find in the documentation. All right, let's have some more fun and start with a simple portal tutorial that will retrieve and display a difference image. ADQL is probably something you're now familiar with from the past sessions of the Data Academy. This particular ADQL statement will retrieve an R-band difference image that overlaps the center coordinates of the extended Chandra Deep Field South, the ECDFS field. So you can see this particular ADQL query selects all of the key columns from the OBSCOR table where the image overlaps the central location of ECDFS, that's 53 minus 28. And then it makes some settings, setting the calibration level to 3, using a subtype for the data product of difference image. And then there's this weird one down there where instead of just saying R, band equals R, the way things are stored in the OBSCOR table is these like min and max values of the spectral range that's covered by the image. So I'm going to show you, so how would you know that R band is this number? I will show you how to figure that out. So come with me into the portal. So just in case you are brand new, logging into the Rubin Science platform at data.lsst.cloud is the URL. Click on portal to take you into the portal aspect and you will land here. We are going to be querying for DP1 images. So we select the DP1 images tab. Wonderful. You'll notice that all of the key columns that are recommended to use with the OBSCOR table are already selected for you. Great. Let's come over to the constraints half. We do want to constrain the observation type and source, which means we want to constrain the type of image that we are querying for. Coads and difference images, we want a difference image, set that as level 3. For instrument name, it's Data Preview 1 is ComCam, Data Preview 1 is the only thing that's available. And again, at level 3, we want difference images, not coads. So we select the difference image. Scrolling down on the left, we do want to say observation boundary contains points, so that we want a difference image that contains this particular coordinates, the center of the ECDFS field. And then under spectral coverage, filter by bands, R band only. And so from here, now that we've set up our query, we could simply search from here, but instead click on this populate and edit ADQL button, and it will take you and convert the user interface query that you just put together into an ADQL query. And this shows up in a bit of a different order, but it is exactly the same as the one that I was showing you in the slide. And you can see here, it's converted for you your request for an R band into how ADQL takes in a request for R band. So once you're here, you can click on search. All right. So here it has returned to us 182 difference images that have overlapped the coordinates that we asked for in the R band. Just going to make this a little bit broader. And you can see, oh, this is an interesting, our coordinates are right at the edge. So if you can just see the yellow, yellow is not very visible. There, you can see better now the brown marks that are search location. So we just picked a random coordinate kind of in the center of ECDFS, but probably your science use case for doing something like this would be some kind of weird photometry that you noticed and you wanted to come and check out what that particular DIA source looked like in the difference image, for example. So the little marker would show you your search location. Okay, great. It's just a very simple example of how to get at a difference image in the portal. Just pausing, looking at the chat for questions. Don't see any hands up. Nothing in the chat. Okay. All right, let's do our next example, which is plotting a light curve in the portal. And here we're using ADQL again, and I just want to give you kind of a better look at this ADQL statement. There's a lot going on in here. So this is, we're using some advanced ADQL. This statement, this ADQL query, searches for a DA object at a given coordinates and then retrieves its force photometry light curve using a table join to force source on DI object and also joining to the visit table at the same time. So this is a triple join advanced ADQL statement. I just want to break it down a bit. So you can take a closer look. So up top, we've got the select statement where these are the columns that we're selecting from each of the tables. Our main query is on DIA object table. This is how all of your queries for light curves should start. Don't want to do spatial queries on force source. You don't want to do spatial queries either on DIA source. They have many, many, many more rows. So the proper way to do it is to do your spatial query on just DIA object and then grab all of the associated photometry points from the other tables to go with that particular DIA object. So that's what our main query is on, DI object. You can notice we're using the as to give our table a short name. That helps a lot, especially when you're selecting multiple columns from multiple tables. You can specify from DIO table, I want the RA, the DEC, and the DI object ID. And we're joining on the force source on DI object table so that we get force photometry back. Remember, this is recommended for light curves. And here we're joining on DIA object ID. So we're retrieving all of the forced photometry measurements for a given DIA object ID. The second join that happens is to the visit table. And here we are matching for every measurement that matches a DIA object ID in the force source table. That forced measurement will be associated with some visit because it's being made in a particular difference image. And then we want to go and grab the MJD time for that particular visit from yet another table. So this is pulling together data from multiple tables, all with one statement. The actual query part, like the constraints part that's happening, is happening on the DIA object table, and it's primarily happening with this statement where we are looking for very specific coordinates with a small radius. So this particular query is the case where you know there's a time domain object, maybe it's your favorite object or an object you've been studying before, something that you saw on transient name server, or there was an ATEL about it. You have the coordinates for a time domain object on the sky and you want to go and get its light curve from Rubin. That is the use case scenario here. So we're searching DI object to get the DI object at that very particular coordinates, and then joining with these two other tables so that we get all the force flux measurements and the exposure, the MJDs. And one further limitation that we have in this query is that we're saying, actually, we only want the R band forced photometry measurement. So this is just going to build us a forced photometry light curve in R band. I'm pausing to see for questions. All right. This one, since we're not starting with the UI, I'll paste it into the chat. Can come here, back into the portal. This time it's a catalog query. This time we're going straight to ADQL. So yes, you could convert this into a magnitude, but I will show you why that's not a good idea for difference image fluxes once you see the light curve itself. So we'll paste the ADQL in there. So we've got our forced fluxes back in the table, 116 images with forced flux. It has over, so this particular window at upper left, it's still showing our last query. So I'm just going to take that out. We are not that interested in that. We are more interested in making a plot. So the reason why I said don't convert this to magnitude, you can see right away the difference image fluxes are sometimes negative, which is why it's best in the time domain when you're working with difference image photometry, you stay in fluxes and don't convert to magnitudes. We're going to switch this plot. So I'm going to create a whole new one. New scatter plot where the x-axis is time and the y-axis is flux. And there is our light curve. So you can see a bunch of fluxes do go negative. So actually two things to notice. One is that since we haven't applied any flags, there are some spurious measurements here that flags would probably get rid of. I'm going to zoom. I want to zoom in. No, that wasn't the zoom in. Why is this being weird? Probably because it's a live demo. That's what I wanted to do. Okay. Okay, zoomed in on the flux, and you can see that here the object is detected with positive flux in the difference image, and then after this midpoint, it is detected with negative fluxes. So in this particular case for this object, it becomes negative flux in the difference image when it is fainter than it is in the template image. So I had mentioned before for data preview 1, because the template images were made out of the same batch of images, the difference images are being made out of time domain objects appear in the template. And so, for example, if this is a supernova, it could be, that appears in the template image, you know, it's going to have some flux in the template and that gets subtracted off. So as the object fades, once it is fainter in a visit image than it is in the template image, the fluxes go negative. So yes, if you're using direct fluxes, then usually it's fine. But even so, with forced photometry, because forced flux measurements get made whether there's an object there or not, and because the images are background subtracted, you can have forced fluxes even in direct images that are a little tiny bit negative because they are around 0. So you can still run into issues where if you try to convert to magnitude, like a whole set of fluxes, that you'll sometimes miss epochs because that conversion won't happen when the flux is negative. All right, those are our two portal tutorials. Let's move over into the notebook aspect. And if you remember, you start at data.lsst.cloud, go into the notebook aspect. It will look something like this when you get in there. You will have the usual welcome page up, but if you've been here for the first two sessions, you already have this going. So the first tutorial we're going to work through is 306_1. So under the tutorials menu, data preview 1, 300 level, 306 series on extragalactic transients, and then the 306.1 tutorial on transient light curves. Open that up. It will look like this. A reminder, you can switch to the notebook table of contents using the left-hand sidebar. All right. You get started by importing a few packages, just matplotlib for plotting, and the tap service is all we need here. Instantiate the tap service, assert that it exists. We're good to go. We're going to use the standard LSST colors that we've selected to represent each of the filters. These colors have been selected for being colorblind friendly, and so we use them everywhere. All right, we are set up. And now we want to retrieve light curve data. As I mentioned a few times, for light curves, it is best to use the force source on DI object table, because then you get photometry measurements from all of the difference images, not just the ones in which it was detected. So the key columns here are the PSF diff flux column, that's the forced PSF photometry on the difference image. The DI object ID we've talked about is the unique DI object identifier. You always want to retrieve the band so that you know what color to put on your point in the light curve plot. And we need to get also the visit is another key column from force source on DI object, because we need to join to the visit table so that we can get the MJD, so that we can eventually make our plot of PSF diff flux versus MJD, just like we did in the portal. All fluxes are measured in nanojanskis and not in magnitudes, because as we've been discussing, negative flux measurements would then just be emitted if you convert to magnitude, so you start missing data, which isn't good. All right, this particular example, very similar, I think exactly the same as what we just did in the portal, where we define the RA index of a known transient. In this case, it's a known astrophysical transient that was in data preview 1. Define a small search radius of 1 arcseconds and to convert it to degrees. We put together our, so in the portal, I kind of showed you the more advanced query first with the triple join. Here in the notebook, it does it in separate steps. So first we query for this particular, these particular coordinates in the DI object table to get the DI object ID. So we're kind of doing it in 2 steps. So first, setting up a query on the DI object table to see if there was an object, a difference image, a time domain object at that location. And it turns out, yes, there was, and we can get the DI object ID. And once we have that, then the second step goes to the forced source on DI object table to retrieve the light curve and join it with the visit table. So you can see this here also looks similar to the ADQL query that we did in the portal. It's just we've separated out, instead of doing a triple join, we did one query on DI object table, and then we do another with a single join between force source on DI object and visit. So we define the DI object ID that we want, set up our query to get the light curve for it, and run it. And one of the reasons why I like to show it both ways is there could be cases where your colleague just gives you a DI object ID and says, hey, go look at the light curve for this particular object ID. And then you can copy paste this exact ADQL and use it. All right, we've pulled out our table of force source measurements. Let's just take a look at the table. So these are all the coordinates that we asked for from force source on DI object. So you can see PSF diff flux has come back and it is negative in a bunch of cases. And in this case, we haven't restricted to R band only. We've got G, R, and I measurements at least in there and some Z band as well. So the light curve that we end up plotting in this example will be multi-band, whereas in the portal, we were doing R band only. Okay, let's take this table away. And then we plot the light curve. So this just, yeah, some standard use of matplotlib to put the light curve together. And so you can see R band is the upside down red triangles. And you can see them here. This is similar as to what we retrieved in the portal. But in this case, we've obtained data for all 6 bands. So you can see it here. And you can see the same thing where some fluxes are positive and then they go negative over time once the object fades below the brightness that it had in the template image. I want to do, so this is actually, if you got a copy of this notebook, this is where that notebook ends. It just grabs data and plots a light curve, but I wanted to do a few extra things with you. I wanted to show you why we recommend that you use the forced photometry light curve instead of the detections that are in the DIA source table. So it is much easier to query DIA source. I mean, you can see just from the ADQL, much simpler. You don't have to join to the visit table because midpoint MJD times were included in DIA source. So it can be very tempting. Let's go ahead and get the same light curve, but the detections only. So not the forced photometry light curve, but just signal to noise ratio greater than 5 detections in difference images. We'll get that from the TAP service. All right, so 253 detections total. And then in this particular panel, I'm going to replot the force photometry and then plot detections only side by side so you can see the difference. So the top is the same as before. It's the force photometry flux measurements only. But then on the bottom, this is what happens when you query the DIA source table instead and only get detections. You have missing epochs where the source was had a signal to noise ratio less than 5 in that particular difference image. And so it was never detected, which means that photometry was never recorded. So you end up missing some epochs entirely. And you can tell, especially in the G band over here, you end up missing a lot. And in the case of time domain objects, even when it has a flux around 0, which is what the gray line is in each of those, because it's a difference image, like a flux of 0 is still very informative. It just means it's the same flux as in the science image as in the template image. When it has similar flux in the science and template image, you end up with a flux around 0 in the difference image. And that can still be useful information for time domain objects. So non-detections aren't not information when it comes to time domain astronomy and difference images. So I wanted to make this point that this is why we recommend using the force source table instead. I'm going to do a brief pause. I don't see any questions or any hands. All right. To wrap up, I want to show you what's in the next tutorial in this series, which is candidate transient identification. So the first tutorials and all the other ones that we did today are all for a single object. You knew the RA and DEC already. You somehow knew this object was of interest to you, and you just wanted to get the light curve. That's that use case. But of course, there will be other use cases where you're trying to find objects of interest to you. You're trying to find things that vary in a certain way, that maybe have a certain rise and fall, a certain slope decline. Basically, you want to come to the DI objects table, use these time series features to constrain all the DI objects down to ones that vary in a way that's consistent with your target population to find candidate objects of the type you're interested in. So this tutorial is a good place to start if you're looking to figure out how to do that. And for example, in this case, it tries to find a bunch of light curves that sort of vary, kind of like type 1a supernovae. So I've gone through and I've already executed a lot of the cells because I just want to show you kind of quickly what this does in case you're interested in working through it later. What it first does, it gets a sample of GI objects. There is, it's in the 305 series on galactic transients and variables. You will find a periodogram example in there, and I'm sure someone can tell you specifically in the chat. This has just grabbed a bunch of DI objects and is investigating their time series features, plotting a couple of histograms of what, for example, the distribution of minimum and maximum values and the slope values are, just to start to get familiar with what these time series features are. And then it makes this like little filter sort of for type 1a candidates that just says things like any DI object that's not near this flux saturation limit has at least 10 R-band detections. The R-band flux is fading at a specific rate that kind of matches the type 1a supernova light curve, and it has an amplitude that's greater than its mean flux. So it's showing significant amounts of variation over time. These are very rough examples, almost quite vague, but similar to what you might want to make for finding your own kind of objects. If you do make these kinds of cuts on the time series features for DI objects, you can see it goes down from our original query, just pulled over around 200,000 DI objects as a first example. And with just these little constraints, it cuts it down to 13 type 1a supernova candidates, as in might have light curves like a type 1a supernova. And then it goes through, 13 is enough to just do a visual review. So it just kind of plots the light curves so that you can take a look. I think this one here is our friend that we were using for all of the other examples in this tutorial. There, you can see it's got a declining light curve. Our simple cuts have pulled out another one that's pretty similar situation. So this is just showing you a place to get started when you're trying to identify groups of objects in the DI objects table. I wanted to skip section 4 and then just show you also that this particular notebook shows you a way to make image triplets for an object that you're interested in. So cutouts, I think, have been covered in other sessions. And this notebook applies as an application of the cutout service where it defines a little function to use. It says, I want to make an image triplet of this particular candidate. Goes through, uses the SIA image service to set up, finding all of the images that it wants to make cutouts from, getting everything all set up, making the cutouts from all of the images. It needs to warp the template to be rotated and matched to the science image, and then eventually displays it. So this is the example triplet. I think it's the exact same one that I was using in the slides as well. The very common kind of thing that time domain astronomers want to look at. So an easy way to make a detection triplet. And that is where I wanted to end today's tutorials, just to give you those tools. As a reminder, please fill out our exit survey for this session. And stick around after the break if you want to talk more, and we'll cover whatever you need to know. I think we got all the chat questions.